my name is Nader Mehimpe. I'm a professor and IRC chair at the University of Calgary, Department of Chemical and Petroleum Engineering. I mean, I was listening to most of the lectures. I mean, it sounds that my presentation in next 15 minutes or so might be a bit different. Although I enjoyed all of your lectures, cyberbullying, bullying. I mean, these are the very social problems, and I enjoyed listening to it. But this presentation is a bit more engineering science related. So what I can do, I can promise to make it as simple as possible. But again, you can ask me later on if there is any questions. Thank you very much. So this has to do with preparation of aerogel supports for methane chemical looping combustion CLC processes. You know, I'm going to discuss the preparation and then the chemical looping combustion data, and then I make a very brief conclusion at the end. I mean, from the other side of the sustainability and environmental impact, so the greenhouse gases, as we know, are making their footprints in our daily life. Where I'm living in Canada is in province of Alberta. We have a lot of gas emission. It's a very energy-rich province, so we have lots of oil and gas and also other industries there. As you can see in this graph, is about 44% globally. I mean, might be different country by country, provinces by provinces, cities by cities, is responsibility for the electricity generation. Then we have manufacturing. Then we have fuel combustion. We had road transport. There are different. They have different portion of the emission. In Alberta, obviously, is electricity one, because we are consuming about 60% coal in our power generation, and also oil and gas, and also other energy sectors. So generally speaking, I mean, CO2 capture, CO2 is is a gas, is a greenhouse gas. Responsible is the most abundant one in the earth. So there are three general ways to capture. We call it post-combustion, pre-combustion, oxy-fuel. Post-combustion is when you produce the CO2 and then you try to deal with it afterwards. Pre-combustion is when before you produce syngas or any other gases to send it for combustion for producing the energy. So you try to deal with the CO2. And the oxy-fuel combustion is when you use pure oxygen. As a matter of using pure oxygen, you produce kind of a very high concentration CO2 that allows you to separate the CO2 very easily, because the other gas would be vapor, water vapor. You can easily condense in, and then you end up with the pure CO2, which is very desirable, because then you can sequester or do whatever with it. So the chemical looping is related to oxy-fuel. In oxy-fuel, you need, as I mentioned in this one, so you need pure oxygen. Getting pure oxygen is very difficult and very, very costly. Air separation is different technology on that one. So what we are doing in chemical looping, we are using material that they can donate oxygen and then goes through the combustion extreme, and then after that one you try to regenerate the material by providing the oxygen to it in another reactor. We call it air reactor versus the fuel reactor. I don't get to the detail of that one, but just to let you know that the oxidation of metal happens in the air chamber or air reactor, and usually we are dealing with a very high temperature. In the fuel reactor, we introduce the fuel in order to get the CO2 and also the other gases for further processes. In a nutshell, so what you do, the CLC process, also we are working on the reforming process as well. So you get the heat out of the second reactor, and then you can produce a steam for a steam generator for the electricity production. Also, you can use, as I mentioned, you go to the reforming route and then produce syngas and hydrogen, which is a different ball game. And I don't get to detail of that one. I'll just focus on the CLC today. So what we are today briefly, what I'm going to discuss the aerogel material that we are using. If you remember, I mentioned the oxygen carriers are solid materials that they are circulating between these two reactors, and then therefore eliminates the provisions of air or oxygen. So basically, the oxygen through the process is obtained from these solid materials. Those solid materials is called oxygen carriers. So the material that we are using as an aerogel preparation was a patent that we made with one of my postdocs. So it sounds very promising because it creates a lot of physical properties that is very desirable for oxygen carriers. So aerogel, that's the terminology. I'm going to just mention in next slide what are those and how you're going to make it. Usually they give us a very high surface area. I mean, just the number is 500 meters squared per gram. Gives a very high pore volume, like about 2 cc per gram. Is a very low density, and all is creating a very small size particles. We call it nano size particles. Is usually is less than 500 nanometer. So the way that we make it is we prepare it. We go through. If you use water, we call it hydrogel. If you use alcohol, it's called it alcogel, obviously. And depending on the drying process, it's called extragel or aerogel. If you go through a slow drying process, it's called extragel. The one that we are using we call it aerogel, is going through a supercritical fast drying. We just, with a high pressure, we try to do it very quickly. And then that's what you get your aerogel as a result of that supercritical fast drying. So again, I don't get to the detail of that one. So as an example, you can use metal alkoxide. So you dissolve it in alcohol and then you hydrolyze it. When we say hydrolyze, you add water into it very slowly, and as a result, it gets hydrolyzed, and then you get the desirable molecules, in this case MOH, and then they react and they make your aerogel. This cartoon shows a little bit of how things are getting conducted. So in a nutshell, again, as I mentioned, so you make your aluminum and your solvent, then you solve it, and then you hydrolyze it, you dry it, calcinate it, and then you make your aerogel. Again, this is another way of showing it. Just again, just to let you know how we are making the aerogel. So you make your soles and then you age it, and then you make the gel, and then you dry it, supercritical drying. You make your aerogel, and then this would be your support. So then you impregnate what you need to do. Like for example, you need the nickel oxide, you need the iron oxide, or in another case we use the potassium carbonate for carbon capture. So then it sits on that support and then makes your material. Either is a catalyst, is a oxygen carrier. So that shows a cartoon. That's how extragel and aerogel are looks like. So this is a XRD. We just when we show that one, that means that they are very amorphous structure, and that's what the structure of aerogel we expect it to have. Otherwise, we shouldn't have that kind of disparity and the changes in the XRD images. So that's a ACM image that shows that they are kind of a very light, fluffy structure they have. As I mentioned, they are very light, density is very low, and they are very nanopore materials. These are the material that we made. I mean, like we made different temperature, different materials. So the samples that we made, like I'm going to mention what are those, is A1, A2, A3. So the significance of that one is the surface area that you see is about in the somewhere between 1,500 to 2,000 meters squared per gram. And these are all desirable properties when we are talking about the support that contributes to the oxygen properties of the oxygen carriers. So this image shows a kind of a nitrogen adsorption desorption isotherm for aluminum aerogel. Basically, by these ones you can find what kind of textural characters you have. Like we have different types, type 1, 2, 3, 4. And when you know the type of the material, then you can estimate the oxygen capacity of the system. So when we go to the, this section was had to do with the preparation of the aerogel. The next section, basically we use the thermogravity analysis to see how it's working in the oxygen transfer between the fuel. And then that's what we have, as I mentioned, we use the nickel oxide and ferrous oxide for this matter. We impregnated on the aerogel and we made the materials for our experiments. You can use different method like the co-precipitation, incipience, wetness impregnation. So we use the impregnation method to impregnate the nickel or iron on the aerogel. So for example, you see some of the samples that we prepared, like for example 60% nickel oxide, but different temperature. And also the ferrous oxide, again, with the different temperature. And then that shows the oxygen carrier, the oxygen content of this material. The higher the oxygen content is better for us, and then basically it provides more oxygen to the fuel. So these are the TGA thermogravity analyzers. So TGA is a small equipment. We use it in the lab. We introduce the material and we circulate different gases, and then based on the change in the weight, we can have some estimation of how things are progressing. So in this graph, we introduce the methane first, and then that goes through the oxidation of the methane, and then in the next round, when the oxygen carriers for example, let's say is nickel oxide, becomes nickel. So we have to oxidize that one to produce oxygen to the structure again. So that's what we introduce the oxygen or air, in this case, oxygen, and then we purge the inert gas, and then again goes through that loop, this methane, oxygen, and then also the inert gas. So that shows how things are progressing with respect to the nickel oxide. So what you see, these small peaks over here, these are what we call it Koch formation. This has to do with the nature of the oxygen carrier. So nickel oxides are prone to produce a lot of coke. Cokes is bad. So the reason is bad because it creates a very solid carbon layers, and then you need to remove that one. So ideally you want to have zero coke formation. That's what our research was. We had another presentation this morning that we showed that we can use other metals to reduce the coke formation almost to zero. Like for example, you can use tungsten to bring it to zero. These are different temperature. As you see, like for example, the higher the temperature, the previous one was 700. This is 800. And then you see as your temperature increases, the coke formation enhances as well. And this is another oxygen carrier. I mean, we use a ferrous oxide here. So ferrous oxide is much less coke producing rather than the nickel oxide. So in conclusion, preparation of alumina aerogel, that's what we showed. There, we have done other aerogels as well, like zirconia aerogel, silica aerogel. But in this presentation, I just presented alumina aerogel. So that showed the properties that I mentioned about in terms of the surface area and the density and the pore diameter. So this seems to be desirable for to be linked to the oxygen carrier, basically acts as a support for the oxygen carrier. And then we use the impregnation method to impregnate the material, whatever is that, like is a nickel or iron, into the support. And then we did the experiments, and you saw that how this gets done. So all in all, what we are doing in this research, we are trying to find the optimal conditions and the best oxygen carriers for chemical looping combustion. So, and chemical looping combustion sounds to be a very promising technology for carbon capture. And the bottleneck of this technology is the oxygen carriers. If we can have desirable and optimal material for this technology, basically we can push the technology to the commercialization. So that said, I'm gonna thank my postdoc, Dr. Karami, who we did the job, and then we created a patent out of this work, and also all members of my groups which are not available today. I mean, not all of them. I have a large research group at the university and the ERGs. And thanks to NSERC, as Natural Science and Engineering Research Council of Canada, for providing funding, and also industrial funds from our old companies like Canadian Natural and Devon. Thank you very much.